Welcome to Julia for Talented Amateurs, where I make wholesome Julia tutorials for talented amateurs everywhere. I am your host, the Dabbling Doggo.
I dabble.
Last week, I gave a course overview, and we installed Julia, Atom, and Juno onto our local computer. We also wrote our first line of code, Hello World. If you haven't watched last week's tutorial yet, stop and watch that tutorial first. The link is in the description below. Otherwise, I am assuming that you all have Julia, Atom, and Juno installed on your computer, and you're ready to go. Today, I will be asking and answering some fundamental what is questions before we begin coding. For example, what is a computer? What is a program? What is a programming language? And finally, what is Julia?
What is a computer?
I'm a computer. I'm a computery guy.
We all know what a computer is, right? We use one every day, but what is it really? I mean, not physically, but conceptually. What is it? The concept of the modern stored program computer can be traced back to the English computer scientist Alan Turing. He published a paper in the 1930s that included his theoretical notion of a universal machine, which we now know as a universal Turing machine. In the early 20th century, mathematicians were exploring whether or not it would be possible to solve any calculation following a set of rules. In other words, they were trying to answer the question, is it possible to teach a machine to perform any calculation, or is this a skill that only humans can possess? Prior to Turing, some academics had concluded that it was not theoretically possible. However, Turing presented proof that it would be possible to create such a machine. His stroke of genius was to propose writing down information in a coded form. He described his theoretical machine as storing a fixed set of instructions, or an algorithm, or a program, for the problem that it was trying to solve. This machine would also have an infinitely long magnetic tape that ran along a tape head that could read or write onto this tape. For its language, the tape head would only use a 0 or a 1 or a blank space. The tape would then move left or right to go on to the next step of the predefined program. Turing argued that, in theory, such a machine could be built, and that it could solve any calculation with a simple set of instructions and a simple set of actions, all by using just zeros and ones. Conceptually, this is how computers work today. Modern computers are nothing more than calculating machines that follow a simple set of instructions that is stored in memory, and it performs these calculations using a simple set of tools, all with just zeros and ones. It's amazing to think that Turing dreamed up this machine in a world where conventional wisdom said that it was theoretically impossible. In the 1940s, Alan Turing's vision became reality. In 1945, a Hungarian-American computer scientist named John von Neumann came up with his design of a practical stored memory computer. His design is known today as the von Neumann architecture. His design consisted of a memory unit, which contains data and a sequence of instructions, and a central processing unit, or a CPU. The CPU houses a control unit, which contains an instruction register and a program counter, plus an arithmetic/logic unit, or ALU, which does primitive operations. And finally, for human interaction, allowances are made for inputs and outputs. Although this architecture was designed in the 1940s, all modern computers still follow this design today. Computers have gotten smaller, faster, and more powerful, but its heritage can be traced back to the 1930s and the 1940s. So when we ask, what is a computer? Conceptually, this is a computer.
What is a computer program?
A computer program, or simply a program, is a sequence of instructions stored inside a computer. It's built from a predefined set of primitive instructions. For example, it can perform arithmetic and logic operations. It can perform simple tests. It can move data. A special program executes each instruction in sequence. It uses tests to change flow of control through sequence, and then it stops when all the steps have been completed.
What is the difference between a program and an app?
An application, or an app, is just a computer program with a user interface.
What is computational thinking?
Computational thinking is a set of problem-solving methods that involve expressing problems and their solutions in ways that computers can execute. When applying computational thinking, practitioners are designing algorithms that get computers to do the work, and modeling the world through the lens of information processes. Computational thinking is characterized by the 3 A's of computational thinking, which is an iterative process based on the following stages: abstraction, automation, and analyses. We'll use the Wikipedia example of how does a mudslide work? So in the abstraction stage, the question is asked in general terms, i.e., how does a mudslide work? Well, I don't know, so let's try to get the computer to figure it out. In the automation stage, we create a computer model to run simulations. So we allow for factors such as gravity, soil conditions, the amount of rain, etc. And then in the analysis stage, we run the model to make predictions and analyze the results against real-world data. And then this process is repeated or iterated as necessary. In the MIT lectures, this final stage is called algorithms.
What is an algorithm?
An algorithm is like a recipe. It is a set of steps that accomplishes a task.
What is computer science?
Computer science is the study of computers, both in theory and in practice. It includes both hardware and software, as well as networking and the internet. Learning how to program is only one aspect of computer science.
What is a computer programming language?
Computer programs are written using one or more computer programming language. Conceptually, a computer programming language is an abstraction of natural human language that we use to control the behavior of computers. All computer programming languages ultimately boil down to a set of primitive operations that are used to create recipes for computers to follow. Alan Turing showed that you can compute anything using just 6 primitives: read, write, erase, left, right, halt. In theory, anything that you can compute in one language, you should be able to compute in any other programming language. Using these primitive operations, programmers can create expressions. Expressions are complex but legal combinations of primitives in a language. Expressions and computations have values and meanings in a language. Valid expressions must be syntactically correct and semantically correct. What does that mean? Expressions must be syntactically valid. So for example, the expression quote-unquote doggo space 3.14, this syntax is not valid, whereas in the example 3.14 times 4, the syntax is valid. Syntactically valid expressions must also have meaning. So for example, quote-unquote doggo plus 3.14, this syntax is valid, but this expression has no meaning. Whereas 3.14 times 4, this syntax is valid, and this expression has meaning. Thus, it is syntactically and semantically correct.
What is a low-level programming language versus a high-level programming language?
Any programming language that resembles the computer's internal instruction set is said to be a low-level programming language. Assembly language and machine language are 2 typical examples of low-level programming languages. This is an example from the chipmaker Intel of the low-level language that their CPU understands. A programming language that offers high generalization from the computer's internal instruction set is called a high-level programming language. Typically, a high-level programming language has elements resembling natural human language to make programming easier.
What is Julia?
Julia is a high-level programming language. Julia is a relatively new programming language that is free and open source. Julia was created by these 4 gentlemen in 2009. Reading their names from left to right in this photograph are the founders Stefan Karpinski, Viral Shah, Jeff Bezanson, and Alan Edelman. I apologize if I mispronounced any of their names. They released version 0.0 in 2012. Version 1.0 was released in August of 2018. All programming languages fall somewhere in this matrix when comparing speed to relative ease of use. Starting in the lower left corner are the cursed programming languages, the languages that are both difficult to use and super slow. In the lower right corner are programming languages that are super fast but difficult to use. In the upper left corner are programming languages that are user-friendly but kind of slow. And finally, in the upper right corner are programming languages that are both easy to use and super fast. These are the unicorn languages. I am not aware of any programming languages that are in the lower left corner. since who would use a language that is both difficult to use and super slow? If you know of such a language, let me know in the comments below. C is a very fast language, but it's difficult to use, so it goes in the lower right corner. Python is easy to use, but it's kind of slow, so it goes in the upper left corner. Most programming languages fall somewhere in the spectrum between C and Python. Finally, the upper right corner has always been considered a myth. The conventional wisdom was that if you wanted a fast programming language, it had to be easy for your computer to understand. So, by necessity, it would be more difficult for humans to understand. On the flip side, if you wanted a programming language that was easy for humans to understand, it would have to be slow because it would require all sorts of extra steps in order to convert the human-readable code into something a computer could understand. And then Julia came along. The creators of Julia claim that their language is both easy to use and super fast. How were the creators of Julia able to do this when so many other programming languages could not deliver this combination? Later in this tutorial series, we'll take a look under the hood of Julia to see how they did it. Julia is well suited for the modern world that is increasingly reliant on such emerging fields as data science, big data, artificial intelligence, and high-performance computing. As for me, an amateur and a hobbyist, I like Julia because it's fun and it's free. Okay, enough lecturing. Let's do some coding. Double-click on the Atom shortcut to start Atom. If you get a message asking to register Atom as the default Atom URL handler, click Yes Always. If you didn't get this message, don't worry about it. I've used Atom since the last tutorial and I got this message, but forgot to take a screenshot. Click anywhere in the REPL panel, hit Enter to start up the REPL. Once that's done, you can adjust the right side panels by dragging the vertical bar. Click in the REPL and type in 1 plus 1. In this example, the plus sign is called the operator, and the numbers on either side are called the operands. Before we go further, just a note about learning to code. You cannot learn to code passively. When I type in code, you should pause the video and type in the code yourself. When this tutorial is over, you should spend some time on your own by practicing. You will only get out what you put in. An easy way to practice is to take my code and modify it slightly to see what you get. A big part of learning to code is muscle memory, not only for your brain, but for your fingertips as well. Throughout these tutorials, you will use every single key on the keyboard. Some characters you may have never used before in normal typing, so I highly encourage you to practice. Practice, practice, practice. Like most things in life, the more you practice, the easier it gets. When you type in 1 space plus space 1, those spaces are called white space in computing. Alternatively, you could have typed 1 plus 1 with no space, 1 plus space 1, and still get a 2, 1 space plus 1, still get a 2, and 1, lots of spaces, plus lots of spaces, 1, and you still get 2. You can even type 1 plus, enter, 2 plus, enter, 3, enter, and you'll get 6. For the most part, Julia doesn't care about white space. However, despite this flexibility, as a best practice, you should leave 1 space between the operator and the operands for readability purposes. Later in this tutorial series, I'll share a style guide that contains some best practices for how you should type in your code. Here are some other basic math operators. This is 2 minus 1. Of course, that's 1. This is 2 times 3. The star key is over the number 8. And that's 6. And this is 4 divided by 2, which is 2. And this is 5 divided by 2, which is 2.5. This character is called a caret, C-A-R-E-T, and it's over the number 6 on your keyboard. Julia uses the caret for exponents. So 2 caret 2, this is read 2 to the power of 2, or 2 squared. Note there is no space in between the operator and the operands in this case. So that's 4, and that's because it's the same thing as 2 times 2, which is 4. 2 caret 3, this is read 2 to the power of 3, or 2 cubed. And that's 8, and that's because that's the same as 2 times 2 times 2, which is also 8. There is no percent operator in Julia. On your calculator, the percent sign is really just a formatting change. For example, 5% is just a different format for 0.05. In Julia, the percent sign is used to calculate the remainder when two numbers are divided by each other. In computing, this is called the modulo operation. The Julia documentation simply refers to the percent character as the remainder operator. The percent character is over the number 5 on your keyboard. So this is read 4 modulo 2, and that equals 0. And that's because when you take 4 divided by 2, the remainder is 0. And this is read 5 modulo 2, and that equals 1. And that's because when you take 5 and you divide by 2, the remainder is 1. If you're a computer programmer, this is nothing new. However, if you're a normie like me, this is a little weird. We'll find out later that the remainder operator is actually very useful, but it will take some getting used to. Please excuse my dear Aunt Sally. Do they still teach this in elementary school? When I was a kid, we were taught, please excuse my dear Aunt Sally, to remember the order of operations. I don't remember the names of any of my teachers, but for some reason, I still remember this mnemonic device. Please excuse my dear Aunt Sally stands for parentheses, exponents, multiplication/division, addition/subtraction. As expected, Julia follows the order of operations. In this example, Julia comes up with 6481. So how did Julia figure that out? Following the order of operations, Julia would do parentheses first. So what's in the parentheses is 2 times 3. So that equals 6, right? So now you have the expression 1 plus 6 to the 4th power times 5 is what you're left with. And in this expression, Julia would do exponents next because there are no parentheses left. So what's the exponent? It's 6 to the 4th power. 6 to the 4th power is 1296. So now you're left with the expression 1 plus 1296 times 5. And when Julia looks at this expression, it's going to do multiplication or division next because there are no parentheses, there are no exponents. The next thing on the list is multiplication or division. Julia is going to go 1296 times 5, and that's 6480. Now all you're left with is 1 plus 6480, and that, of course, is 6481. As you might expect, Julia follows the order of operations, and for clarity, you can always add more parentheses, since Julia will do the parentheses first, but you should never use square brackets. These square brackets have a special use in Julia, which we'll cover later. Before we go forward, just a side note on the parentheses and the quotes. You may have noticed that I entered double parentheses and double quotes, and then I used the left and right arrow keys to get in and out of them. I realize that this is not normally how people type, but for coding, this is a common defensive coding technique to avoid making syntax errors, because it's very common to forget the closing parenthesis or the closing quote when you're coding. Typing this way is not required, it's just a suggestion. The term Boolean is named after George Boole, who created Boolean algebra in the 1800s, where the results to problems were either true or false, rather than a numeric value. So in this example, this is read, is 3 greater than 2? And of course the answer is true, because 3 is greater than 2. The greater than sign is over the period on your keyboard. This example is read, is 2 greater than 3? And of course the answer is false. In this example, this is read, is 3 greater than or equal to 3? Of course the answer is true, because 3 is equal to 3. In this example, this is read, is 2 greater than or equal to 3? Of course the answer is false. And same thing happens on the flip side. So this is read, is 2 less than 3? The less than sign is over the comma on your keyboard. And again, this is read, is 3 less than 2? Of course, that's false. And this is read, is 3 less than or equal to 3? And that's true. This is read, is 3 less than or equal to 2? And of course that's false. There's also an equality. This is read, is 4 equal in value to 2 times 2? And note that there are 2 equal signs. And of course the answer is true, because 2 times 2 is equal to 4. And this is read, is 2 times 2 not equal in value to 4? And the answer is false, because of course they equal each other. This is a little unusual to see. This is the exclamation point equals equals. That is the not equal in value. This is called the short-circuiting Boolean AND. This returns true if both sides are true. Otherwise, it returns false. This character is called ampersand, and it's located over the number 7. This is going to answer the question, are both sides true? So, are both sides true? And of course, that's true. In this example, are both sides true? Of course, that's false. Are both sides true? No, that's false. Same question. Are both sides true? Of course, that's false. This is called a short-circuiting Boolean OR. This returns true if either side is true. Otherwise, it returns false. This character is called by many names. In Unicode, it's called broken bar or broken vertical bar, sometimes called pipe. Whatever you call it, it's the vertical line on the right side of your keyboard between Enter and backspace. And the way you get to it is by Shift \. This is asking the question, is either side true? And of course the answer is true, because at least one side is true. Right? They're both true. So again, asking the same question, is either side true? And it's true, because at least one side is true. Same question, is either side true? And of course, it's true, because at least one side is true. Same question, is either side true? And of course, it's false, because neither side is true. Another interesting thing about Booleans is that true and false actually have numeric values. This is read, is false equal in value to 0? The answer is true, because in Julia, false is equal to 0. So the question here is, does true equal in value to 1? The answer is true, because in Julia, true is equal to 1. So because true and false have numeric values, you can actually use them as operands like any other number. False plus false is the same as 0 plus 0. So you should get 0, which you do. So false plus true is the same as 0 plus 1. And of course you get 1. True plus false is the same as 1 plus 0. Of course you get 1. True plus true is the same as 1 plus 1. So of course you get 2. This can come in handy when you're trying to figure out how many true statements there are on a long list. You don't need to count them individually, you just add them up. These may seem like simple examples, but these are the basic building blocks that we will use to create very complex programs. That's it for today. If you made it this far, congratulations on successfully getting through the basics.
Proud of you, son.
Today, we asked and answered a lot of what is questions. By doing so, we established a foundation of computer science knowledge that we can use to build upon as we learn to program using Julia. After that, we used Adam to play with some basic math and logic operations. Next week, we'll explore the concepts of variables, expressions, memory, and types. If you enjoyed this video and you feel like you learned something new, please give it a thumbs up. For more wholesome Julia tutorials, please be sure to subscribe and hit that bell. If you have any questions, please post them in the comments below, or send me an email at julia4ta@gmail.com. I will be uploading a video on Sundays to answer questions that may come up. Feel free to spread the word by sharing this video, since I'm sure you'll all agree that this is the finest tutorial on all of YouTube.
Worst
Tutorial.
ever.